Hello everyone, I am Julia Cicada and I am representing Fluence Analytics in today's presentation on automated polymer reaction monitoring, analysis, and control for manufacturing optimization. And this talk will be focusing on ACOMP, Fluence's main project. Polymer manufacturing is a $1 trillion a year industry, and it is roughly split in half between polyolefins, polyethylene, polypropylene, and their derivative copolymers, and other polymers, polystyrene, polyacrylates, polyamides, polyesters, vinyl chlorides, water-soluble polymers, their copolymers, and much more. These materials are everywhere in modern life and serve as a wide range of applications in home and personal care, medical supplies, construction, consumer goods, and much more. Polymer manufacturing, however, lacks standardization and optimization. A lot of these processes are the same as when they were invented decades ago. And there are even differences among different sites of the same company that are nominally making the same product. Smart manufacturing for polymer production has lagged other areas in the chemical industry due to the intrinsic challenges when it comes to direct, real-time online measurement of the reaction mixture, which can be inhomogeneous, very viscous, and require high pressures and temperatures. The majority of companies still rely on a worker to manually extract aliquots, often exposing themselves to hazardous conditions, and then transport the sample to the quality control laboratory for traditional analysis with offline techniques. Once the characterization of the material is complete, however, it provides information about what was in the reactor hours ago, which leads to control strategies and decisions being made with stale data. This traditional method can turn into a lot of unwanted costs for industries, as they lead to off-spec product, poor control of production, deviations of quality, and reduced efficiency. There is a lot of R&D activity towards more automated, safe, continuous characterization methods, mostly comprising of in situ calorimetric rheological sensors, especially those involving Raman and infrared spectroscopy. Those techniques, although useful, are usually model-dependent for interpretation of the data and are subject to harsh reactor environments. Even though inferential models have also been successfully deployed in industry and continue to evolve, they still do not provide direct data on polymer properties, making them not optimal as a control tool for targeting specific polymer characteristics. The solution we propose in that context is ACOMP, which is a technique that has been developed and improved for the past 20 years as a viable, versatile option. ACOMP stands for Automatic Continuous Online Monitoring of Polymerization Reactions, and it is a non-chromatographic technique that relies on continuously extracted reactor content that is appropriately conditioned and automatically goes through multiple sensors, whose raw data are then analyzed and valuable parameters about the reaction are readily available for the operator through Fluence's proprietary software. This dataset can be used for production optimization, plant digitization, reduced cycle times, improved yields, and consistency. The material is essentially born characterized once it's ready. Overall, such automatic real-time online monitoring technique allows companies to progress in four main fronts: reduce cost and gain market share, streamline processes and drive efficiencies, improve quality and development of new products, as well as meet their sustainability goals by reducing waste and environmental footprint. This can be achieved as ACOMP allows for saving time in each batch cycle, leading to more production capacity available, reduces the need for analytical testing and thus manual sampling, as well as overtime, allows the operators to stop production before degradation of products, and allows the R&D to develop new products faster. Most importantly, according to the world trend concerning global warming and more sustainable practices, this is an opportunity for companies to reduce their energy consumption and lower volatile organic compounds emissions. Now going into more details on the technical aspects of ACOMP. The system basically comprises of what we call the front end, where the reactor is mounted with a recirculation loop to ensure that the reactor content extracted is representative of what's actually happening inside the reactor. An extraction pump is attached to it to continuously extract small amounts of reactor contents that then goes through whatever conditioning is necessary, such as diluting, quenching, or breaking emulsions. Once it reaches analytical grade, it moves into the detector train, the backend, that can be customized depending on the application needs and have a variety of detectors such as ultraviolet visible spectrometer, light scattering, viscometer, refractive index detector, conductivity meter, infrared spectrometer, etc. All this raw data is collected throughout the reaction, as it can be seen on the plot in the middle, and based on some reference values, solvent and monomer baselines, many parameters are automatically calculated, such as monomer and polymer concentrations, conversion, cumulative and instantaneous molecular weight, intrinsic and reduced viscosity, and copolymer composition. These parameters are responsible for the final polymer material properties, such as strength, brittleness, melt temperature, solubility, etc. Therefore, monitoring polymer properties during synthesis is the first step towards achieving control of the production of tailored polymers. Industrially, ACOMP has been successfully used in the past to monitor solution, emulsion, and bulk reactions. Through its automation software and analytical detectors, it makes both raw and process data available for operators in a very user-friendly software. It has been historically used to monitor batch, semi-batch, and continuous processes for a wide range of applications, such as elastomers, water-soluble polymers, engineering plastics, adhesives, paints and coatings, and more, as these are continuously being expanded thanks to Fluence's applications engineering team. Now going into some case studies. For solution styrene butadiene rubber industrial production, ACOMP allows for identification of the coupling reaction in real time through three main calculated parameters from the multi-angle light scattering and the viscometer units, molecular weight, and low and high shear reduced viscosity. As we can see on the plot, this reaction has two main phases. Up to 3600 seconds into the reaction, what can be seen is the natural increase in the polymer chains as the reaction progresses, which is consistent with monomer consumption and shows the living character of the reaction, a monotonic increase in signals as the propagating chains are alive. After the coupling agent is added, the second half of the reaction shows another significant increase on these values, consistent with these polymer chains formed before being brought together through coupling, quickly reaching their final specifications of molecular weight. Continuous monitoring allows to establish the optimal point for addition of the coupling agent, for example, earlier, after observation that the first plateau has been reached, based on the desired final molecular weight, and detect shear thinning or thickening behavior, as they are directly related to processing and rheological properties. Another important application of the ACOMP technique regards tracking residual monomer. For many applications, such as for polyacrylamide production to be in spec for use in consumer goods, there are regulations that restrict the amount of monomer that can be left in the final product. Given the real-time character of ACOMP analysis, it allows for operators to detect that residual monomer has reached an ideal threshold earlier than it would be possible with discrete offline analysis. Here on the plot, we can see the monomer concentration calculated from the UV measurements as it decreases exponentially throughout time as the reduced viscosity increases as the polymer chains increase. These are all indicative of the reaction progressing and monomer conversion. We can see here that from the usual method of manual extraction of aliquots followed by offline characterization, the confirmation that the minimum residual monomer threshold in parts per million has been achieved comes at least 1.5 hours after what has been detected with ACOMP. In this case, if the reaction is stopped earlier, both money and time can be saved, as no further conversion is necessary and a more consistent product quality can also be achieved. Polymethyl or PMMA, is a well-known lighter and more impact-resistant alternative to glass, as it is also transparent and weather-resistant. Its synthesis can be in bulk, in emulsion, or in solution, like on the data depicted here. Cross-linking becomes necessary in order to increase material ductility and reach higher glass transition temperatures, which can be important for certain medical and energy storage applications. Here, we can see the comparison of molecular weight calculated by ACOMP during monitoring of solution polymerization of methyl methacrylate with and without the cross-linker. ACOMP may also help when assessing optimal cross-linker amount for desired molecular weight, as well as optimal cross-linker addition time, allowing for easy visual inspection of the results in real time and fewer reactions. Moving on into the lab scale for R&D and academic research, the ACOMP system can offer many advantages for scientists, such as studying polymerization kinetics in few experiments, scaling up processes to pilot scale, a customized detector train for various chemistries, actively controlling of reactions, and possibly integrating it with more traditional methods for polymer characterization, such as gel permeation chromatography if desired. As mentioned before, through continuous monitoring, it is easy to study reaction kinetics when certain variables are altered. On this project, we've studied the copolymerization of acrylamide and sodium styrene sulfonate to compare free and control radical approaches, here referred to as FRC and RAFT respectively. The first thing observed, as we can see on the left plot, was that as the initial sodium styrene sulfonate content increases, the slower the conversion of acrylamide gets, which led to the hypothesis that acrylamide is initialized more easily by the initiator, but then prefers to transfer radical to the other monomer instead of polymerizing. And once sodium styrene sulfonate reaches a certain minimum threshold, acrylamide polymerization progresses with normal speed and exponential decay. On the right side, we show the comparison of the same reaction carried out with FRC and RAFT, and we have found that the kinetics are virtually the same, but that the characteristic molecular weight trend is very distinct. A monotonic decrease can be seen for FRC, where the chains initiate, propagate, and die very quickly, and a monotonic increase for RAFT, living chains propagating simultaneously throughout the entire reaction. Given this stark difference, real-time monitoring can also help operators in industry visually inspect bad batches where control has been lost, saving money and time. The continuous nature of these quantities obtained with ACOMP is actually what enables for a non-model dependent controller. Here, we present the first results of molecular weight control during acrylamide free radical solution homopolymerization. As we can see on the left, the molecular weight trend now was forced to resemble the monotonic increase seen for RAFT, which contrasts dramatically with the batch uncontrolled trend also shown on the plot. The control interface developed in-house reads the continuously fed data from ACOMP measurements, compares the control variables with the target trajectory, seen in red on the plot of the left, and sends the appropriate feedback command back to ACOMP hardware, telling it to pump more monomers, chain transfer agent, initiator, etc., depending on the control strategy chosen. In this case, feed pumps were set to pump in acrylamide monomer at desired flow rate. Further developing the controller, the next step focused on using a controlled feed of chain transfer agent to obtain a desired molecular weight distribution. And on this project, a trimodal population was successfully obtained in one pot, as opposed to the traditional industrial way that would require mixing different grades of polymers obtained from separate batches. And just to show the robustness of the controller, on the plot on the right, we see the temperature being manually altered by the operator, and we can see how the controller was still able to follow the target trajectory for molecular weight. This is because of the non-model dependent character of the controller that is theoretically suitable for any chemistry and can adapt given unforeseen circumstances with ease and accuracy. Now going into composition control, a free radical copolymerization of again acrylamide and sodium styrene sulfonate was carried out. Now, the controller was successfully capable of keeping the sodium styrene sulfonate instantaneous fraction within the 0.5 target trajectory. And we can see how it compares to the strong compositional drift seen for the uncontrolled reaction. Last, molecular weight and composition control were achieved simultaneously, now with a more challenging trimodal trajectory for composition, while keeping molecular weight constant, as we can see on the plot on the right. Current efforts focus on using this controller against raft copolymerization to automatically obtain gradient copolymers with desired composition distribution. Efforts to expand the types of detectors available to be used as part of the detector train have also been successful with the coupling of a Fourier transform infrared detector with a flow cell. This is critical as we expand the range of monomer combinations that can be successfully monitored, as a lot of the polyacrylates in industry are actually copolymers. Acrylate monomers can have almost identical UV spectra, so individual concentrations are not possible to be calculated with that technique only. But slight differences in the monomeric structure lead to different vibrations on the IR region that can be tracked, like it has been done here for the isomeric pair tert-butyracrylate and N-butyracrylate. From the two characteristic absorption peaks indicated on the plots, their individual concentrations were calculated and composition can be tracked. In summary, such automatic real-time online monitoring technique applied in industrial production can lead to increased yield and plant capacity, improved product quality, accelerated scale-up and development of new products, decreased energy consumption and raw materials waste. In R&D or the lab, it can help with kinetic studies and ultimately be critical for on-demand polymer manufacturing through reaction control. Overall, real-time continuous data allows companies to cut down inefficiencies in production and thus save time and money that could be turned into higher production volume, thus higher in-spec volume that can be sold. Thank you for your attention. Feel free to reach us out through the Fluence Analytics website if you have any questions or just want more information about the technologies we offer. Have a great day.